Okay, so let me continue the last lecture. So in the last lecture, we have introduced reversibility, and in that lecture, we were talking about Amoroso algorithm. So in Amoroso algorithm, there are two parts. So one algorithm is for testing bijectivity, and another is for injectivity. So in last day, we have discussed about subjectivity test. So today I continue with injectivity test. Well, although so the Amoroso algorithm, there are two parts, but if you're asked to decide reversibility, then testing of injectivity is sufficient. Because we have seen that injectivity of a cell automaton implies subjectivity, hence injectivity implies biactivity, and biactivity in case of CA is synonymous with the reversibility. So testing of injectivity is sufficient to testing of the reversibility. So since we are discussing reversibility, so if you want, you may not test bijectivity. You will not test subjectivity of a cellular automaton. To test bijectivity, injectivity, this test is sufficient. Please. Okay. So, so the here intuitive idea is, so how we can proceed. So the way is we have to find many to one mapping, right, in the CA. So you have many configurations. If we find two configurations, they are mapped to a single configuration, then it shows that there is a many to one mapping, right? So it means the CA is not injective. So the idea is consider all possible configurations, and somehow you search if there exist two configurations which are mapped to a single configuration. If we are successful in in that search, means if we get two configurations, then we say okay, it is not injective. But if we fail to get such two configurations, we call it injective. Take this example. So the example we have taken in last day. In subjectivity test, we proceed with these two with this automaton. So so consider two configurations, all 0 and all 1, right? And then you find just I've taken two arbitrary configurations, all 0 and all 1. Then try to find out this next configuration. What we'll find? See here, so 0 0 0. You can see that see the rule here is 0 0 0 is mapped to 0, and 1 1 1 is also mapped to 0. So if you consider this two way, let me use the jam again, so it will be easier. Okay, so here what I'm doing here, what I'm doing here. So suppose, so we have 0 0 0 0 in this configuration, so all 0. Then we are having here say 1 1 1 1, etc. Right. So now here, so all 0 all 1. So here 0 0 0 0, this is 0. Okay, then again 0 0 0, it is 0. Because why it is 0? Because in my rule table we have get that this for against this one 0 0 0, I'm having 0. So in this way I'll get 0, all 0, right? So if 0 0 is my previous configuration, from that 0 0 0 I can move to this all configuration. Now come to this one. Here, what I find 1 1 1, consider it's a thing about CA. Okay, a cell depends on its left neighbor and right neighbor that I have considered. So it's thin about CA. So you consider three consecutive, consecutive positions. So it's 1 1 1. What is 1 1 1? For 1 1 1 in that rule, you'll have 0, right? So again 1 1 1, for this next 1 1 1, you'll have 0. In this way. So you will have all 0 here. So what I get, so if you have these two configuration, all 0 and all 1, all 0 and all 1, they both are mapped to all 0 configuration. So this is I mean, if we search to configuration, so we are successful here. In this case, we are successful. We get two configurations. One is all 0, one is all 1, which are mapped to a single configuration. So if we get such a mapping, it means there is a many-tone mapping. It means the CA, the given CA, is not injective. Right. So the idea, so this simple example I have taken because these two are homogeneous configuration, so all 0 all 1, right? So what is the idea in this way? So this idea you have to follow, that you have to find two configurations, right? Say I'm saying that it is say A1, then A2, right, then A3. In this way I am finding, say is one configuration, and then another configuration I am finding, say B1, so I am finding B1. So here say I am using say B1, then B2, then B3 of then say then B3, then B4, etc. How I am finding? So my intuitive idea is, so I am finding two configurations like A1, A2, A3, A4, etc. B1, B2, B3, B4, etc. such that these are configurations, they are mapped to same configurations. So how can I know this one? So I can think of an algorithm where, see, A1, A2, A3, if I'm considering on three neighborhood CA, three neighborhood, cell automaton. So a cell depends on three neighbors only. So in my domain, in my domain of rule, there are three elements like A1, A2, A3. Suppose I am constructing an algorithm in this fashion that A1, A2, A3 and B1, B2, B3, they map to say same element. Say both are mapping say C1, say. Just I'm taking an example that they are mapping to C1, both are mapping to C1. Then I am moving one room right. Say then what I am getting? Say I am getting say A2, A3, A4, and suppose it is mapped to say C2. And here B2, B3, B4, say I am taking say B2, B3, B4, suppose these B2, B3 before they are mapped to C2. So my intuitive idea is I want to construct two configurations, A1, A2, A3, A4, A5, etc. One configuration, another is B1, B2, B3, B4, B5, etc. in such a fashion that these I can get C1, C2, C3, this next configuration. So how can I construct these two configuration? Rule table is given to me, right? Rule table is given to me, and I'm considering the next value, right? I'm considering the next values of each entries, and then I'm clubbing them. If I get A1, A2, A3 having C1 and B1, B2, B3 again having C1, right? So A1, A2, A3 and B1, B2, B3 both are having C1. So then I can start these two string A1, A2, A3 and B1, B2, B3. Then I'm extending. So from A1, A2, A3, I'm trying to get A2, A2, A3, A4 and B2, B3, B4, so that both of them A2, A3, B4, both the pattern A2, A3, A4 as well as B2, B3, B4, they're having same image in the rule table. Now in this way, if I able to construct two configuration, then I'm done. So I can say that there is a many-to-one mapping, right? And if I fail to construct such two configurations in all possible ways, I will try all possible ways. If I fail to construct such two configurations, then I'll say it is injective. So exactly this idea, this idea is used by Amoroso Patt algorithm. Recall that our CA is infinite. So we have infinitely many configurations, right? So you cannot pick up two arbitrary configurations and then you can test. So you need some smarter way, right? So that you have to you will explore finitely many configurations, and based on that you'll be able to decide whether it's injective, whether it's not, right? Is the idea clear? So let me repeat it again. So in the idea, the style is, recall that in case of surjectivity test, which we have covered in last day, we try to find predecessor of configurations, right? So if I find two predecessor against one configuration, so I'll saying it is subject, if I say no configuration against, no predecessor against a configuration, we say it's not subjective. So in that case, we were searching predecessor. Here, we were considering successors or next configuration. And what is the idea? Idea is search for two configurations so that they are mapped to a single configuration. So this idea was used in this injectivity test of Amoroso and Patt. Now start the algorithm. So here what is given? Given an arbitrary local map, so R, S to the power m to S. What is S? S is the the state set. We are considering its coordinate is D, and M is a neighborhood. Okay, a cell depends on M neighbors, so this is M, and R is the local rule. Okay, and from that we get a CA called a parallel map. Recall that when we were discussing parallel map in the first day, in the first day of this course, so we are talking about that, if the local rule, the local map, right, or if in the time we have used the F is not surjective, can the parallel map be surjective? That question is posed in first class. Okay, and at the time I said there exists algorithm which will tell us how to decide I mean, a parallel map is injective when the given rule is not injective. See here, R is not injective. It cannot be, right? R is not injective because in the domain it has, I mean, d to the power m entries, whereas in codomain there's only d entries, right? From this definition you can understand. Here you have s to the power, m entries, s to the power, m entries here, right? Sorry, d to the power m entries in the domain, and in codomain there are only d entries. So it is, d is always non-injective. But when R is non-injective, I am constructing our parallel map G using data. Can it be injective? That was the challenge for parallel map. So this algorithm, test that injectivity. So I shall explain this algorithm by giving an example. First, you partition the rule in maximal classes with same image under R, right? With same image under R. What I'm saying, that suppose image means, R of say one tuple, suppose it is 0. For another tuple, R of that tuple is again 0. So these two tuples are coupled, right? So in this way, we we partition the table, rule table. Now one more point is there. We have proved before, Professor Kari has proved this, that if a rule is not balanced, it cannot be surjective. So if it is not surjective, it cannot be bijective. And here injectivity implies bijectivity. So we have excluded the rules which are not balanced. You can test also with this balanced rule, there will be no problem, and then you'll be able to see that, okay, algorithm is giving, it's not injective. So here you can assume that R is balanced. In my example, I have considered an R which is balanced. So if it is balanced, and if you have D elements in S, you'll have D classes, and each will have d to the power m-1 members. And for each of the D classes, construct a sequent table. So what is the meaning of sequent table? I'll tell you. With arbitrary ordering of that members of the class. Suppose say in maximal classes like this: alpha 1, alpha 2, alpha 3, alpha 4. So R of alpha 1 is equal to R of alpha 2 is equal to R of alpha 3 is equal to R of alpha 4. Means they have same image. Suppose you are having so. So now I form a table like this in this way. So along with the x-axis, I am writing here alpha 1, alpha 2, alpha 3, and along with the y-axis, I don't repeat with alpha 1. I repeat with alpha 2, alpha 3, alpha 4. Now this order doesn't matter. You can start with alpha 1, alpha 3, alpha 2. Here alpha 4, alpha 2, alpha 3. This doesn't matter. But you have to form this kind of table, which is called as sequent table. Okay. And each box corresponds a unique 2-element subset of some class. Okay. And conversely, to each 2-element subset, there corresponds a box. Okay. So let me give an example that will be clear. Take this here, this local rule. Okay. I have taken this binaries here. This example actually we have taken from Amoroso Patt's paper. In the paper, Amoroso Patt gave this example. Right? So it is a 4 neighborhood CA. So this is all 0 to all 1. So 4 zeros to 4 1. There are 16 entries in the table. Okay. So this next value, you know, it forms the rule. It's my rule. Okay. So all 0, it's 0, 0 0 0 1 is 0, 0 0 1 0 is 1. In this way, you can see that rule. I have taken this rule as an example. Okay. So here d equal to 2, s equal to 0 1, and m equal to 4. You can see the CA is balanced. So count this number of 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 zeros and 8 ones. So the CA is balanced. Right? And you can taste it is subjective. You know, so you consider this is as your home task, and you can see from using the previous algorithm that this CA is surjective. Now, what step 1 was saying of the algorithm? It is saying partition the rule based on their next value. We are having next value 0 and 1. So here 0. So 0 0 0 0 is 0, 0 0 0 1 is 0. 0 0 1 1 is 0, 0 1 1 0 is 0, 1 triple 0 is 0, 1 0 0 1 is 0, 1 0 1 0 is 0, 1 0 1 1 again is 0. So these, you know, entries, okay, they form a single class. See here I have written 0 means I have put a decimal value against this 0 0 0 1. So this is normal style. We normally put decimal equivalent against this, you know, against this neighborhood configuration. So here 0 0 0 0 1 1 1 1 15. So for 0 class is formed by these entries 0 1 3 6 8. So 0 1. This is 3. This is 6. This is 8. This is 9. This is 10. This is 11. 8 and 11. And rest are forming other class. This is 1. This is the first step of the algorithm, right? Now, second step, I have to form the table. We call the table sequent table. So first, there are two. You know, we have two classes. We have received. There are two classes, one for 0 and one for R. So for each one, I have to form a sequent table. We call it sequent table. The name, this name sequent table is given by again Amoroso Patt in the paper. This name they have used. So sequent table for 0, right? Here 0, 1, 3, 6, 8, 9, 10, 11, they are the elements. So I have written in this fashion 0, 1, 3, along with the x-axis 0, 1, 3, 6, 8, 9, 10, right? In the recall that in the alpha 1, alpha 2 I have said in this fashion, right? So if there are say k entries, so along with the x-axis there are k minus 1 entries, and here also in y along with the x-axis there are k minus 1 entries. So 0, 1, 3, 6, 8, and here not from 0 but from 1, 1, 3, 6, 8, 9, 10, 11. Please note that this is arbitrary. I mean, from 1, so this is 1, you can put here 6, you can put here 8, there's a problem. Okay, so we are putting in this way 0, 3. In this way, we are forming a table, right? So same is for 1. So 2, 4, 5, 7, 12, 13, 14. Okay, in this way along x-axis, and 4, 5, 7, 12, 13, 14, 15 along with the y-axis. So we have created two sequent tables. So if you have d number of steps in S, then you'll have d number of entries. Okay, you'll have d number of sequent tables. Now the next task is you have to fill up the sequent tables. Let us fill up. Okay, I have not started this one. Okay. Now, okay. Now, how to fill up the sequence table? Okay. See, let me read again. Read out first. It is saying for each two-element set, alpha beta. What is alpha beta? So alpha is along with the x-axis and beta along with the y-axis. So that box I am referring to. Okay, against alpha beta, I can get a box. Okay, so for this one, I can get another two-element set alpha dash beta dash, and that alpha dash and beta dash is called as sequence set. Okay, for which I'm calling it sequence set. For the first one, alpha beta, I'm calling it sequence set. When, how can I get this alpha dash and beta dash? Some condition is there. Actually, shifting one bit of alpha as well as beta, I am getting alpha dash and beta dash. Just I have given an example. I am just shifting one bit right. In this case, always we shift one bit. Always we allow right shift. So we shift one position right of alpha as well as beta, and then we get alpha dash and beta dash. So what is the condition? Say rightmost m minus 1 symbols of alpha and beta, right, agree with leftmost m minus 1 symbols of alpha dash and beta dash. So that means I'm shifting. If I shift, then then only I can get this kind of match. And most important thing is r of alpha dash is equal to r of beta dash, right? And here alpha and beta, alpha dash and beta dash, they have to be they have to be distinct, right? If they are distinct, then only I can consider the sequence set. Otherwise, it can form a set. So how can I get this one? So left shift alpha beta, as I've said, left shift alpha beta. Here it is written each one with position, and the rightmost position can be filled with any s. I mean any state, any element from S to generate possible alpha dash and beta dash, right? So how can I form this one? Okay. You are getting, maybe I missed one slide where I was forming this one. Where the slide? Well, for example, uh, just a sec, because I have to tell you how can I form this table one. That slide is missed here. Okay, it is here. Okay, it is here. So fill up the tables, sequence tables for 0. So how I am filling up this? How I am filling this sequence table? See, consider the, it will be step 2. It is mistaken. Let me step 2. It will be step 2. Okay. So how I am filling up this? This sequence table. So these 0 and 1, alpha and beta here. Say alpha is 0 and beta is 1. So this set I am considering. So say considering alpha and beta. From this alpha and beta, what I can get? See, let me go back to jam again. So So alpha is 0, 0, 0, 0. And 1 is, beta is, say 0, 0, 0, 1. Right? So that is alpha. And that is beta. Okay. From this alpha and beta, I want to form alpha dash and beta dash. What I shall do, I shall right shift this one. So one bit is shifted. So from that, I can get what I can get, this 0, 0, 0. After shifting one bit right, then I have to fill up the next position with any symbol from this S. In my S, there are two symbols, so 0 and 1. So here I am putting 0. I get this one, and from that one, I can again get, so this 0, 0, 0, and this 1, right? So I am getting from alpha. If I left shift and if I put any value in that hand side, I can get 0, 0, 0, 0, and 0, 0, 0, 1. Similarly, from beta, I can get this one. So here there's this 3. So 0, 0, 1. Then this position I can put 0, and here 0, 0, 1, 1. So from these two, I can get 4 elements, right? This is value 0. So in my table, I wrote it as 0. This is, I wrote it as 0. I wrote it as 1. And here I am getting 0. This is 1. This is 2. And this is 3. Right? So from alpha and beta, I can get this 4. Oh, okay. Now alpha. So these are forming my alpha dash, and these two are forming my beta dash. I mean, anyone can be alpha dash. Anyone of it can be beta dash. So now I want to form a pattern alpha dash and beta dash. Sorry, I have to form a set actually. I want to form a set with alpha dash and beta dash. Okay. What is the condition alpha dash and beta dash? R of alpha dash. What is written there? The condition was R of alpha dash. Sorry, R of alpha dash. It is to be equal to R of beta dash. This is the only condition. Right? Let's see. Come back to this one. Here, what I find, 0 and 3. Right? Alpha 0 and 3. So 3 is here, 0. But I get 2. 2 is 1. So come back here. So I cannot consider this 2. Beta dash, 2 cannot be beta dash. These 2 cannot be beta dash. Okay. So I can get 2 combination, 0, 3. If alpha dash is 0, if it is 0, and if it is 2, then this condition is satisfied. Again, if alpha dash is 0, and beta dash is 3. Sorry. It will not be 2. Yeah. Sorry. So here it is 0 and 3. If it is 0 and 3, then this condition is satisfied. And next, if it is 0 and, sorry, why am I writing 0 and again? So if it is 1 can be alpha dash, because 1 is also 0, and 3 here 1 and 3, then also they're having same next value, right? So I have written here 0, 3 and 1, 3. So from set 0 and 1, I am getting 0, 3 and 1, 3. So in this way, right? So consider 1 and 3 again. See, I shall give one example, one more example, 1 and 3. I'm getting 1 and 3. Okay, come back. 1 and 3. So, it is 1, 0, 0, 0, 1, and here it is beta 3, na? 0, 0, 0. Please let me know if you can understand my handwriting, because I'm using jam and using mouse to write. Okay, so here the similar style from alpha I can get here 0, 0, 1, then 0. This bit is added here, and then I'm getting 0, 0, 1, and 1. This they will form my alpha dash. From this I have to choose an alpha dash, and here I'm getting from this one, if I shift, the leftmost bit will be vanished, and then I'll get 0, 1, 1, then 0, and here 0, 1, 1, 1. So here this will form, they will form my beta dash. And this is, what is this? This is here 2, this is here 3. So alpha dash can be 2 as well as 3. And here I am getting it is 6 and 7. Right? So now I know R of 2, R of 2, R of 2 is 1, and probably R of 7 is 1. Yeah, R of 7 is also 1, is equal to R of 7. Right? So therefore in my set alpha dash, as alpha dash, I can get in my alpha dash I can get this 2 and 7, right? Because they are having same negative value, right? So here see 2 and 7 they are clubbed, and so 3 and 6, so 3 is 0, 6 is again 0. I got 3, so these 3 and 6 they'll form another sequence set. Then 3 and 6 they form another sequence set. But can 2 and 6 form sequence set? No, because 2 is 1, R of 2 is 1, and R of 6 is 0. So they can form cannot form sequence set. So at most I can get 4 sequence set, right? Because 2 and 2 here for this example, at most 2 sequence set I can get. But in this case, in this case, I am getting only 2 sequence set, right? So that is written. That is written here. Sometime I may not get anything. Okay, take 0 and 6. So last example. So here I put cross, because I failed to get any such sequence set. Why I am failing? So take again. Let us take another example. Again, example that 0 and 6. Okay, 0 and 6. Consider 0 and 6. So here 0, 0, and say beta. 6 means 0, 1, 1, 0, right? Yeah, it's 6. So here from this I can get 0, 0, 0, 0, right? And then I can get 0, 0, 0, 1. Similarly from beta I can get 1, 1, 0, 0, and I can get 1, 1, 0, 1. So here this means 0, this means 1, this means 12, right? It's 12, this 13. Possible beta dash 12 and 13, possible alpha dash, right? Possible alpha dash is 0 and there, is 0 and 1, right? Now 0 is RMT 0, 0 here, this alpha, this 0 0 0, it means alpha dash as 0, neighborhood pattern 0 is equal to 0, neighborhood pattern 1 is equal to 0, but 12 and 13 both are 1. You can see, so 0 and 1 are 0, 12 and 13 both are 1. So for this condition, that R of the image of this two pattern, two neighborhood configuration that will be same, this is violated. So you cannot get any sequence set. So I put cost here. So in this way, I have to form the sequence table. So there are d number of sequence tables. In this case, we have two sequence tables for 0 and for 1. If you have d number of states in S, so there will be d number of sequence tables. So you have to fill up the sequence tables in this fashion. Then okay, so that was the sequence table for 0. That's sequence table for 1. Okay, the sequence table for 1 I formed in this fashion. Okay, and there is one more step is there in the algorithm. Okay, if for any set, right, sequence set is itself. Any set means any alpha beta. I'm considering this set alpha 1, alpha 2 is one set. For alpha beta, you can consider alpha beta, no problem. So for any alpha and beta, right, if you see the sequence set is itself, then declare the CA is non-injective. So I get first condition of deciding non-injectivity of a CA. What is this? If a sequence set, what I want to mean here, I can tell you. Suppose in 0 1, I'm saying an example. Suppose in 0 1, you again get a 0 1 here, right? You again get a 0 1 here. So means it's 0 and 1 is alpha beta. Now this alpha beta set you are getting a sequence set 0 and 1 here. If this condition arises, then you declare it as a not injective CA. Okay, so you'll find it means you'll find many to one mapping. Why it is so? You think we shall come back to an example later, right? So in step 2, in the first step, after filling the sequence table, sometime I'll be able to decide non-injectivity of an automaton. Okay. Okay. Now come back. So see, in my algorithm, I have to fill up this table for once. Okay, it's a one-time effort. Then I need to do some processing. That I'm saying the next steps. Step 4 is saying, okay, you have formed this one. Now you reduce the steps. Okay, just sorry, I missed this step. I missed this step, right? Just I have filled it up. Then then some more processing is needed. That actually I have said. So if some box, if in some box there is no sequence set and the box is crossed out. In this the example, I put a X here, right? And this point is interesting. If for some box, say for alpha beta, there exists m tuple y such that rightmost m minus 1 symbol of alpha beta are same. Okay, then we enter for ones and put a star is entered in the box. What does it mean? It means, say from alpha beta I am shifting alpha and beta, but shifting alpha and beta, I get a same set. What is saying here? There exists an m tuple y such that rightmost m minus 1 symbol of alpha and beta, they are same with the leftmost, symbol of y. Okay, so give an example to understand it better way. See here, you see in this example 0 and 8. Okay, in this set 0 and 8 I put a star. Why it is so? So take an example, come back again here. So this is my 0 and consider it's 8. So it is this one. Beta is say 8. So 8 means 1 0 0 0, right? So from this one, what I can get here, so this 3 bit I have shifted here, this 3 bit, I mean after shift I'll use this 3 bit, here also I'll use the 3 bit. What I'm getting 0 0 0 and 0. Here also I'm getting 0 0 0 1. See, this is, I have to choose alpha dash from 0 and 1, I have to choose beta dash from here. Observe that here in both the cases from alpha and beta, I am getting same sets, same possible sets, here 0 and 1. Why I'm getting so? Because these two, last 3 bits here for alpha and last 3 bits for beta, they are same. So if it is same, then after shifting you'll get the same set, right? So how can I decide, how can I get the same set? So if rightmost, so length of this alpha is m, right? This is m actually, this is m, this is m. So if I shift it, so if this rightmost, m minus 1 bits, they're same here. If they become same, then I'll always get the same set, right? So alpha dash and beta dash will be they will be same. Now if I get this one, then I put a star. So it has a good implication, it tells you many things. Actually, it tells where to end my algorithm. So you have to understand it very clearly. And I'm saying, in most of the case, I'm saying that sometime you will get this kind of things. You have to get this kind of things. So you're getting same things here, right? So if I get this, if this condition is satisfied, I put a star, right? So here I put a star, 0 and 8, and 0 and 1, because they are sequence set, because 0 and 1 both are 0, there's no problem, but I put a star here. I put a star here, that is said. Okay, it has implication. So this point, step 3 point, is saying about this one. Okay, now this is a dramatic condition which I have said before. If some sequence set for alpha beta is alpha beta, so as I've said in the examples that the 0 and 1, they'll get, if you get 0 and 1 as sequence set again, then the algorithm terminates. So for sequences alpha and beta, if you get alpha beta itself, then the algorithm terminates. And we conclude that the CA is not injective. Let me come back again. So as I've said that if we find 0 and 1, I'm giving an arbitrary example. So 0 and 1 and one set. For this set, if you get the sequence as 0 and 1 here, you get 0 and 1, 0, 1 here, right? All this is possible for this example. What I'm saying, hypothetically, I'm saying, then I'll say that, the algorithm will terminate and will say that G is not injective. So first injectivity condition, this is the first time I'll be able to decide non-injectivity of arguments here, right? Okay. Now, if we fail to decide non-injectivity, right, then I have to move to the next step. So step 4. Step 4 is saying you reduce each sequent table in the following way. Note that we have already crossed out. We have already crossed out some boxes. We put X. Okay, that's crossed out some boxes. Crossed out means that box, we have not considered that box, the elements of that box for further processing. I want to further cross out some boxes. How? See, if gamma delta is an entry in a box corresponding to alpha beta, and if the box corresponding to gamma delta has crossed out, then put a cross through gamma delta in the box alpha beta, right? So go back in this example. So here, so you see 2 and 12 is crossed out, 2 and 13 crossed out. If in this set, if you find 2 and 12 or 2 and 13, you crossed out. Let me check. Yeah, are you having here 2 and 12 or 2 or 13? No. So if I find it is already crossed out, 2 and 12 is already crossed out, right? Because I put X here, cross here, right? So if it appears as sequence set against any alpha beta, then that 2 and 12 is crossed out. And this process is repeated, right? And in this way, if I be able to, cross out all the entries of alpha beta, then that alpha beta is again considered as crossed out. And this process is repeated again and again. And here, note that you'll find it. If you do it by your hand, you'll find it. Any box containing star is never crossed out. It can't cross out, that one. So, don't consider that star box. It will never be crossed out. So here, this is crossed out. Okay. Say, for example, say 0 and 6. Say, consider this one. I am reducing the sequent table. Say 0 and 6 is crossed out, right? And 0 and 6 appears in 0, 3. It is crossed out. A line is put here. 0 has appeared here. 0, 6 has appeared here. In 0, 11. Cross it out. Out, right? In this way. So 0, 3. Okay. So 0, 6 is crossed out. Fine. Fine. So in this way, let me check. 1, 9 is here X. Where is 1, 9? Here. Okay. And 1 here, 1 and 3. And 2 and 7. 2 and 7. Right. 2 and 7 is crossed out here. 2 and 12. See, look this one. Look this one. 2 and 12 is crossed out. This is sequential table for 0. This is sequential table for 1. Set 1. See, 2 and 12 is crossed out. And 2 and 13 is crossed out. Right? Now here, in this case, you see, for 1 and 6, consider this box. In this box, there is 2 and 12. Since 2 and 12 is crossed out already by the algorithm, so I put a strike here. Put a line here, it's stacked out. So here also 2 and 13 is again here, AX is there. So 2 and 13 is considered. So here I able to put, I able to cross out both the sequence sets of 1 and 6. So then I consider 1 and 6 itself crossed out. Okay, I need not to consider 1 and 6. Now since 1 and 6 is crossed out, okay, here, so here 1 and 6 is crossed out. Now come to the here, 1 and 6 was there. 0 and 6 was crossed out, but 1 and 6 was not before. Now I see that second step, 1 and 6 is crossed out. Then you cross out 1 and 6 again here. Right? So in first level, I cannot cross out 1 and 6. In first level, I can cross out 0 and 6. But in second level, when I see that 1 and 6, all the entries of 1 and 6 are crossed out, then I can cross out 1 and 6. So what I get, 0, 6 was crossed out before. Now 1 and 6, this is crossed out. So whole set 0 and 3, this is crossed out. And 0 and 3 was here. In 0 and 1, so look, 0 and 1, 0 and 0, 3 was there. Now, in second step, 0 and 0, 3 crossed out. So I am putting 0, 3 crossed out. Right? In this way. So I don't want to continue further. I think you have understood that you have to recursively have to do it. It's a recursive procedure to reduce the sequent, tables by crossing out the entries of the tables. Right? Crossing out means for further processing, we shall not consider these entries. Right? And recall that, remember that when we are crossing out the entries, we have to consider all the sequence tables simultaneously. In the example given, I have shown that when I am crossing out some entries of sequence table 0, I have used the sequence table 1, first and 1 actually, right? So this is the step after the next one. Which are remaining? Interestingly, it may have many entries. It was having many entries, but for this example, what were there? We were having 0, 1. Okay. Although I put 0, 1 here because 0, 1 is crossed out because the star was there. Okay. I cannot, omit this part, right? I cannot omit this part because I have, in the algorithm I've said, if a box is marked as star, you cannot, cross it out. You have to remain. You have to consider for further processing. So although 0 and 1, they don't exist. They're crossed out, but I'm putting it. I am keeping it here. So star marked 1, 2, 3, 4. 4 boxes are there. So 4 boxes are considered. Apart from these 4, 2 remain with non-crossed out box, that is 610 for table 0, for sequence table 0 is 610 here. You can see and here it is 214, right? This is also here, right? So these are marked here. Interestingly, there are many entries, all are crossed out, and generally it happens. Okay, generally it happens. We can, cross out many entries. Come back to the step, the algorithm and step 5. It is saying assign a positive integer to each non-crossed out box according to the following rule. Okay, very interesting. So if a box is with star, you assign its weight as 0. Okay. Okay. If you find a sequence set, okay, and then assign its weight as 0. And if the non-crossed out entries in the box corresponding to alpha beta, they have weight like W1, W2, WR, then alpha beta is assigned with the weight as 1 plus, see here, 1 plus maximum of W1, W2, WR. Okay, and that integer, that positive integer, is assigned to that box. And by that rule, it will be able, generally, it will be able to assign integers, positive integers, to the boxes. But in some cases, some boxes may remain, may be left with any value. I mean, it will fail to assign any value. If such arises, if you fail to assign any value, then it's not injective. Okay. So this is the another condition of deciding non-injectivity. First condition, what I have seen. First condition in step 2, step 3. In fact, step 3. What I have seen, that if against an entry against the set alpha beta, if the sequence set is itself, alpha beta is the sequence set, right? We declare the CA is not injective. The second condition I am giving here, if I fail to assign any number following the above rule, it is not injective. So you have to understand why we are calling it non-injective. So only option is declaring, only way is declaring non-injectivity is you have to find 2 configurations which are mapped to a single one. Now suppose there is, and if we get this non-clustered boxes having positive integers, we move to step 7. So here, take this example. Here it is a non-clustered box. Okay, 0, 8, 6, 7. That we have shown before. Okay. Now we assign number. So 0, 8, it was 0, 1. It is assigned 1. Why? The star mark box 0, 1, this is assigned as 0. 0, 1, it is assigned as 0. Right? What is saying? Just a sec. What is saying? That a star symbol is assigned weight 0. Okay, it is the first step. So here 0, 1 is a star symbol, it is assigned 0. So now 08, it contains only one set 01. Based on my scheme, 01 is assigned as 0. So what weight I should assign to 08? The algorithm is 1 plus, what is the algorithm? 1 plus, this is saying, na? This part is saying 1 plus max of W1, W2, W1. Here only one entry is W1 and W1 is 0. So 1 plus 0. So therefore, here 08 is assigned 1. Right? 0 plus 1 is 1. Similarly, for 89, it is assigned 1. For 12, it is assigned 1. 513 assigned 1. 6 following the same rationale. So 715 again assigned 1. Now here for 610, I have two entries. 412. What is 412? 412 is 1. We have already calculated. 513. 513 is already 1. So 1 and 1. So what weight I have to assign for 610? 1 plus max of 1 1. Max of 1 is 1. So 1 plus 1 is 2. So I'm getting 2 here. Similarly, for this one, 412 is 1. 513 is again 1. So 214 is assigned 2. So here, as every box is non-empty, non-clustered box is assigned a positive integer, so we proceed to the next step. We are about to, we're almost done. Step 7. What is saying? Suppose alpha 1, beta 1 is one set, the set, and alpha 2, beta 2 another set, alpha j, beta j another set. The sets correspond to boxes that were assigned integers in step 5. Okay, here I have, so 1, 2, 3, 4, 5, 6. 6 sets are there. Sets are, what are sets? Not the boxes, the entries 08, 6, 10, 2, 14, 4, 12, 5, 13, 7, 15. They are assigned the integers. So I am saying alpha 1, alpha 2, in alpha 1, beta 1, alpha 2, beta 2, them. I am saying them alpha 1, beta 1, etc. Now, if there is an M tuple whose rightmost M minus 1 terms agree with the leftmost M minus term of alpha I and beta I, okay, then G is not injective. Otherwise, G is injective. Interesting. What is saying? It is saying if alpha I and beta I, so read this part, if one of the pairs have same M minus 1 leftmost term, then you declare that it is not injective, otherwise injective. And this is the this concludes the algorithm. Why it is so? What does it mean? Say consider any alpha 1, beta 1. Okay, let me give the example first, then I'll explain. Here we have 8, 0, right? And here I am getting 1, 0, 0, 0, 0, 0, etc. For 14, I am getting this one. Okay, and this one I am getting. Okay, and this one. So what I'm saying here, what the algorithm is saying, if 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 you consider any pair, if you consider any pair and they have same m minus m minus 1 pattern. So here m minus 1 is 1 0 0, but it is 0 0 0, so it's not same. Here 1 1 1, but it is 0, it is 0 1 0 1 0. For this set 1 1 0 0 1 0, they differ. In this way, in all the cases they differ. So here in this example you can see left m minus 1, they differ. So the condition is satisfied. So what I've said, if one of the pairs above have the same m minus 1 and different same m minus 1 terms, then you declare it is not injective. Why it is so? What is the implication? So let me explain with this one. See, if they are same, okay, if if they are same, actually suppose it is say 0 0 0 1, and somehow you have received this one 0 0 0 0. So these m minus 1 terms, they are same. What does it mean? What does it mean? It means from this one, what you have seen here, what you have shown here, you have find two configurations, say two configurations, they are having same, I mean not some configuration, yeah, you have obtained say two patterns actually. In the algorithm finds two patterns, they are mapped to the same subconfiguration. Now if this part is again same, then what was the condition? Please recall. It is saying actually, you can find an m tuple whose rightmost m minus 1 term agree with the leftmost term of alpha I and beta I. So here you can get this one, alpha I and beta I, its leftmost term is same with another m tuple. Then with that m tuple, you can continue with that m tuple. So this part, they are different. For this one, for these two parts are different. They are not same. But from here, if they are same, you can continue constructing an configuration which are same. This part, and this part, they are same. Since this part is same, so next configuration or next states, against this sequence, you will have the same one. For the previous part, you have already shown that they are same. Okay, then it implies you will have two configurations which are mapped to a same one, right? So that is saying here. So therefore, G is not injective. Otherwise, G is injective. So the example we have taken here, the G is injective, the CA is injective. Okay. That concludes the algorithm. So G is injective here. Let me start with let me give another example. Okay. So take this CA. It's rule 30. Again, m equal to 3 here. This example we have taken for subjectivity test. M equal to 3, m equal to 3, right? And is equal to 0, 1, uh, and here and here these are, right? And recall that this CA was proved as subjective, right? Rule 30 was proved as subjective, and this is a balanced rule. Step 1, you there are two symbols, 0 and 1. So two partitions, so two sets we will have, or two classes we will have, one for 0 and for 1. In case of 0, okay, we have 0, 5, 6, 7. See, consider 0. Oh, okay, this is better. Achha, can you see my mouse pointer? Can you see my mouse pointer?
Yes,
Huh?
sir. Yes,
Okay,
sir.
so I think this is better. I can use the mouse pointer at least. So here 0, 0, 0 is 0, and 0, 1, 0, 1 is 0, 1, 1, 0 is 0, and 1, 1, 1 is 0. So it forms. So here is 0 is differential equivalent is 5, this 6 and 7. So against 0 class 0, I have written 0, 5, 6, 7 and plus 1, 1, 2, 3, 4. Right. So sequence table is for 0. I have to prepare the sequence table, right? And the sequence table, right? See here 0, uh, here 0 and 5. If I consider 0, 5, 6, I have written, and 5, 6, 7, and 0 and 5, you can get 1 and 2. I'm not showing how I'm getting 0 and 1 and 2. Okay, should I show 0 and 5 why I'm getting 1 and 2? From 0 and 5, I can get into two sets, 1 and 2, 1, 3. So same one, same way. So let me show from 0 and 5. This is 0, my alpha. From this 0, I'll get 0, 0, 0, and 0, 0, 1, and beta 5. 5 means 101, right? 101. From 101, I'll be able to get 0, 1, 0 and 0, 1, 1. So it is 0, it is 1, it is 2, it is 3. So this is alpha dash. From this, I have to choose alpha dash. Here I have to choose beta dash, right? So here 0 and 2. Here I know 1 and 2. This will form a sequence set because 1 and 2 both are having a next value 1, and 1 and 3. See here. So here is 1 and 2 and 1 and 3. Okay, so it forms because 1 and 2 both are 1 and 1 and 3 both are 1, right? So in this way I form the sequence table, right? This is for 0 and 5, this for sequence table for 0, this for sequence table for 1. Okay, and I get a sequence set. So some two entries are crossed, right? See one interesting, say consider 0 and 7. Consider 0 and 7. I'll give example, another example. Okay, I'm giving example for 0 and 7. For 0 and 7, you'll find interesting one. So what is 7? 1, 1, 1. From 1, you'll get 1, 1, 0. And sorry, you'll get 1, 1, 1. Now this is forming, this forming beta dash, right? Now here 0, 0, 0 is 0 and 1, 1, 0. So you get this set. So this is 0 and 1, right? And here this is again, this is actually again 6. This is 6 and this is 7, right? And what we'll have, we will have this sequence set as 0 and 7, 0 and 6, because 0 for this neighbor configuration 0 and 6 both are 0 against the rule 30, and here 0 and 7. You can see 0 and 6, 0 and 7. Here it is written, say 0 and 6 and 0 and 7, right? That is written here, 0 and 6 and 0 and 7. Consider the step 2 or step 3. What I'm saying, against 0 and 7, it's a set. I am getting sequence set 0 and 7. So the step was, if alpha beta is a set against alpha beta, if I get alpha beta sequence set, declare it as non-injective CA. So very simple one. So in second step, in third step, I can declare it. So here 0 and set, 0 and 7, I get it. And the sequence set, and it is declared at non-injective one. What does it mean actually? So let me tell you. So what does it imply? I am getting 0, 7 in both. The first step I am getting a sequence set as the set itself. What is meaning? See, in this case if you consider two configurations all 0, what will get? So all 0. You are getting all 0. What will get? What is the next configuration of all 0? It is all 0. Right? It is all 0. Why all 0? Because it is 0. In this case, it is 0. Right? So for these three you are getting 0. Next 3 you are getting 0, and so on. So you will get all 0. Now consider all 1. So next step. So this, if I need out 1, 1, 1. What is 1, 1, 1? For 1 on 1 it is 0. In the rule table 1 on 1 is 0. So here I am getting 0. For next 1 on 1 I am getting 0. Next 1 on 1 I am getting 0. Since it is all 1 configuration, says everywhere it is all 1. So I am getting all 0. Right? So all 1, 2 I am getting again all 0. So all 0 I am getting original configuration. From all one configuration, I am getting original configuration. So it's one-to-one map. Actually, this is saying that one. Step 2, right? Step 3, when I'm getting same sequence set, it is saying these kind of things. So if you repeat it again, right? So you actually receive a repetition from 017, from actually what does sequence table does, right? So everything in all the construction of this sequence table, we club those in about pattern which are giving same same image, right? Here 0, this neighborhood pattern 0 and neighborhood pattern 7, they are nested value same, and the sequence table in the entry of the table, which are called sequence set, they are also nested nested value, they are same. So right, so now if I get this 0 and 7 again, so from this 0 and 7 I can construct a two configurations having same next state, having same next configuration. So it is many to one mapping. So in this way, actually, what I've said in the beginning, what does this algorithm do? It targets to find two configurations, right? It targets to find two configurations having having same next configuration. Here, one interesting point you have to note. What I've said, your configuration is infinite, its length is infinite, but here we are definitely not considering infinite configuration. And if you think about a periodic configuration means same thing is repeated somewhere. We have some sense of that periodicity here, right? Actually, we are testing a finite sequence of states, or we can say we are testing sub-configuration, right? So it's like this. Say I am testing like this one. Say okay. Say say the example. Let me repeat the example again. That A1, A1, A2, A3, A4, A5 in this way. In this way, I am trying to construct a configuration in this way. Another way, another is a B1, B2, B3, B4, B5. So by the sequence table, I'm just looking at, I'm in search of this kind of configuration, right? We are actually in search of this kind of configuration. Now, however, this set, so how I'm constructing this? I'm looking at whether these 2, 3, say A1, A2, A3, and B1, B2, they are same. A2, A3, A4, B2, B3, B4, they are same or not. So what I have to do? I have to consider. So here, sorry, here I'm considering m equal to 3. Actually, in many cases, I'll consider m equal to 3 for simplicity. So the same argument, same rationale is applicable for m equal to k, anyone, for any m actually. So here, so A1, A2, A3, B1, B2, B3 are the same. They are next to same. A2, A3, A4, B2, B3, B4 are the same. What does it imply? It implies you look at the rule, and again against each against the neighborhood pattern, you club them. So how to club? If two patterns have same image against R, you club them. So sequentially we'll see. First, how I'm clubbing? I'm clubbing the patterns having same image. Then I'm trying to construct this configuration. How it is constructed? See, look at this pattern: A1, A2, A3. See, consider this pattern. How I'm looking at it. So as if I have received somehow A1, A2, A3, and B1, B2, B3. They're same. Then from that A1, A2, A3, I'm constructing A2, A3, A4. So as if A1, A2, A3, and B1, B2, B3, they are given to me. And from A1, A2, A3, and B1, B2, B3, I am trying to construct A1, A2, A3, A4, A5, etc. B1, B2, B3, B4, B5, etc. And what is the construction mechanism? From A1, A2, A3, I have shifted one room right. So I am testing I am getting A2, A3, A4. How to put A4? A4 is an element of my S. So I'm looking at every element of S, and then I'm suitably put A4 here. Similarly, I'm suitably put B4 here, and the condition is again same. A2, A3, A4, and B2, B3, B4. No, that will be 7. Now, in this way, I'm constructing, inherently, I'm constructing the configuration. But it is infinite. But there is a hope. What is the hope? So this pattern, the neighborhood pattern is finite. So if I construct in this fashion, after some step, there should be a repetition. There has to be a repetition. Right? So it means, after some step, there will be an end. Right? And that determines many things. Now, in this way, recall that I have put a star. Na? What this star implies? Star implies in the example given, recall that 0 and 8 in the example I have given the star, the star same actually. Alpha dash and beta dash, they are same. I mean, a set of alpha dash, possible alpha dash and possible beta dash, they are same. Right? And it means, so I get someone, say here, some neighborhood pattern, which are same in both the cases. Okay. So using that one, so in this, there is a stopping criteria. Now, in this way, I can get many such patterns: A1, A2, A3, B1, B2, B3, etc. I can club those patterns if possible. So assigning number, it means how many, how can you club? The ways of clubbing, these patterns which are having same image, some image. Right? Anyway, the main idea is we search for such a pattern having, same one. So we try all possible ways. We try with all possible ways. Now, if we fail to get any such pattern, we declare it is injective. Although number of configurations, that they are infinite, but these are resulted from the state set S, and the rule R is one which induces G, the parallel map G. So testing of R is sufficient. Anyway, this is intuitive idea. You please, test it again. Actually, we tested all possible ways. We checked all possible ways for which I can have the same image for the configuration. Let me conclude. So it's correctness. I have said actually about its correctness. First one is algorithm will terminate. Sequence set is finite. Tables are finite. I am just searching a table, so the algorithm will terminate. The first condition of correctness. Second one, so I have tested, we have tested all possible ways of forming, of having same image. Okay, and that is step 2. No, it will be step 3, not step 2. It will be step 3. Step 3 and step 5 and step 7. By these 3 steps, I have given example in step 3 and as well as step 7 how I can get the same image. So therefore, if we fail, okay, and we, I mean, you can prove that. So although I have not given any formal proof, how to test that we have tested all possible ways. So if you think intuitively, by sequence table, I have considered all possible combinations of forming, of forming configurations having same image. If I fail to identify inner miniature mapping in surface injective, so my algorithm finally declares it as injective. So this is your home task to formally prove this part. Okay, you prove this formally. I have said the logic of proving it. You can prove it by contradiction or any other method. But anyway, algorithm is efficient. Why? What is the meaning of efficient in computer science? What do you mean by term the efficient? Efficient means efficient in computer science is a single meaning. If a problem is solvable in polynomial time, it is efficient. So, and it is efficient. You can do it polynomial time, and your size of input is always fixed. Actually, it doesn't depend on lattice size. So algorithm is efficient, and it can efficiently solve this. I mean, test injectivity. Okay, that's all. Let me know if you have any question. I've taken much time today. Any question?
Sir,
Yeah, please.
sir, in the injectivity test, you said that when the box is say 1 0 and if the box includes also 1 0, then it is not injective, right? According to the algorithm.
Yeah, yes.
But sir,
Actually,
why?
this is I mean, 10 will never arise in this case. I've given a
Okay,
so
okay.
07, 10 is intuitively I have said, but 10 will not arise. Huh.
Mm-hmm. But
Okay, 10, yeah.
I mean, if the box includes the same value as it is outside the box, then
Yeah,
it is
07
not.
like this. Yeah, yeah. Here 07 and 07. Yeah.
Yes, 0 7 0 7. And sir, why it is so? Can you tell me
Okay, 07.
why
What is it?
why has it been decided like this?
Okay, so you are starting a configuration with 0.
Hmm.
I mean, say neighbor pattern 0. Okay, let me
Hmm.
construct a. Okay, good one. Let me construct this jam. Oh, yeah, this one. Yeah. So let me construct this one. Say 0 and 7. 0 means, say 0 means, so this is 0. It's a m equal to 3. So 0 means this is 0, no?
Hmm.
And 1 means, sorry, 7 means triple 1.
1.
Okay. So from 0 0 0, what I can get? Again 0 0 0 and 0 0 1, and here 0 1 1 0 and 1 1 1. So I am getting this sequence. So this is 1. So I'm putting 1 0 here. If I put 0, I'm getting again 0. I put again 1 here. I'm getting 7. Okay. So this 0 was mapped to 0. And this 1 is again mapped to 0 here. So they are in same sequence set. So here this 1 is mapped to 0. It has to be, because I have put 0 and 7 in the same class. They are against in a same in a same set. Here 0, here 1 1 1 is again 0. So here this 0. So consider I have started with 0 and 7, and this is 1 1 1. Right? So this 0 means the next 0. 0 7, 0 7, 0 and 7. This is for the sequence table for 0 I get. So from 0 and 7 I get this sequence set 0 7.
Yes.
Right? And this is the set. This is alpha dash. Oh, sorry. This is alpha dash. What happened? This is alpha dash, and this is beta dash. Right? Now here I again get 0 and 7. It is 0 and 7. So previously it was 0 and 7. So if I consider this previous one, then from alpha dash I can get again put another 0 here. Here again another 1. So what I can get here? So again 0, this 0 0 0, again 0. This new one, this 1 1 1, again is 0.
So it has
See,
two pre-images.
so I can put again 0 and repeatedly I can put 0 and 1. So I can get a configuration. So all 0 here, all 0, right? Here all 1. So two configurations I'll get. So map to all 0, and all this both are mapped to all 0. So made to one mapping.
Yes.
Okay.
Okay.
That is the reason. Actually, the same one. So here in the one step I can say. In other cases, in one step I can say. From 0 0, I am getting another one. In our work, we call it RMT sequence. Okay. If you know in your work, for example, we call it RMT sequence. We are forming RMT sequence actually, nothing else.
Yes.
So and for both the sequence, they're having the same next sub configuration. Okay. For each RMT, for each location, the RMTs they're having, same next value. Okay. Yes.
Sir, as you said about RMT sequence, then I can comment one thing.
Please.
So that star, that is like we are taking two equivalent sets. So two equivalent sets. If we take two equivalent sets, then only we can get the sibling set. So sibling
Yeah.
set, they are different. So equivalent set and corresponding sibling set, if both of them are so equivalent set has to be having same value, and equivalent set has to have different values. In that condition only you will be getting star, right?
Yes. 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 Anyway, this RMT sequence, RMT will come in our later classes. Okay. Any more query? So proof of correctness, I have given informally, that you have to do formally.